Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, as always, Ricardo Lopes, and today I'm joined by Dr. Chad Orzel. He's an associate professor in the Department of Physics and Astronomy at Union College in Schenectady, New York, where he teaches a wide range of classes and does research on atomic, molecular, and optical physics. And today we're going to focus on his latest book, A Brief History of Timekeeping. There it is, the science of marking time from Stonehenge to atomic clocks. So, Dr. Orzel, thank you so much for taking the time to come on the show. It's a real pleasure to everyone.
Thank you for having me. These things are fun.
Yeah, sure. So, first of all, is timekeeping a human universal? Do we know if all studied or known human societies have some sort of timekeeping?
Absolutely. Like every culture that we have decent records of has some sort of timekeeping element built into it. And there's even arguments that the drive to keep track of time goes back, tens of thousands of years. There's you can find people holding up as an example of the first calendar. There's like a bone fragment from like 40,000 years ago that has these sort of crescent shapes etched into it that people point to and say, well, those are moon shapes. And this is a mnemonic device for, tracking the phase of the moon through the course of a month. So, people have always been keeping track of time. The oldest things that are really unambiguously clocks are things that are solstice markers that are, 5,000 years old, give or take. These sort of monumental structures that people built to mark the position of the rising and setting sun on particular dates.
So we'll probably not get into all the different types of clocks you explore in the book. I'm not sure if we will have time to cover all of them, but generally speaking, I mean, is it that all clocks, I mean, all pieces of technology we used and use to keep track of time have traits in common?
Yeah, I would say that the thing that defines a clock, really broadly speaking, is a clock is something that ticks. And I don't mean necessarily an audible tick like a
Right.
mechanical pendulum clock, but just some regular repeated motion that you count to mark the passage of time. So, an actual ticking mechanical clock, what you're counting is a pendulum that swings back and forth or a mass on a spring that's oscillating. And you count the oscillations and you say, well, so many of these is this amount of time. You can do the same process on a much slower scale with something like the motion of the sun. We're recording this in December, so the days in the Northern Hemisphere are extremely short, right? And then they'll get longer and longer through the year and then come back. And accompanying that, the sun moves across the horizon, returning to the same rising and setting position after 1 year. And you can use that as a tick. You can mark the passage of years by, when has the sun come to these particular positions. And then you can also go in the other direction and look at things that tick incredibly fast, like the oscillations of microwaves emitted by cesium atoms, which is the basis for the modern definition of the second, which is 9,192,631,770 oscillations of a particular frequency of microwaves emitted when cesium atoms flip from one electronic state to another.
Mm-hmm. In what ways, for example, have people been using the movements, quote unquote, of course, of the sun to keep track of time?
So the two big ones are you can measure the passage of time through the course of a day using a sundial. So you basically just take a stick and hammer it into the ground. And if you look at the shadow, you'll see, as the sun appears to move from east to west across the sky, the shadow will track from west to east across the face of the sundial. And that leads to a way to keep track of the time. You can say, well, when the shadow is pointing here, it is this time of day. And when it comes back around, we'll say that's been one full day. The other one is that motion of the sun along the horizon, right? Right now in the Northern Hemisphere, the sun is very close to the southernmost point at which it rises and the southernmost point at which it sets. And in June, it'll be close to the northernmost point at which it rises and the northernmost point at which it sets. And you can use that motion to mark out the passage of a year. So those are the two major motions of the sun, and both of them have been used for timekeeping purposes.
Right. And how do people use the sun to orient themselves in space? And does that have anything to do with the time as well?
Yeah, there's a very deep connection between sort of where you are and what time it is, right? So that takes a couple of forms. One is, the exact trajectory that the sun follows across the sky depends on your latitude, right? So if you are, as we are in the mid, 40 something degree latitudes, in the northern hemisphere, right, the sun is always to the south of the zenith, of the maximum point in the sky. If you go much farther north than we are, you get to a point where there are some days, there's periods of weeks or months even, when the sun is always in the sky, right? And there's periods where it's never in the sky, where it's below the horizon for 24 hours or whole days and weeks. And if you go farther south, you go into the tropical zone, there will be days when the sun is directly overhead. So that also comes into play as to, relating where you are to what time it appears to be, if you're looking at something like the shadow of the sun. Then there's also the issue of longitude, which is people at different points on the surface of the rotating Earth will see the sun at different positions because, of course, the sun isn't actually moving, we're moving, right?
Right.
As the planet rotates, someone who is further to the east will see the sun being further along in its daily apparent motion than someone who's further to the west. And so if you're marking time by the angle of the shadow of the sun, you would say it's different times in those two places. So there's this very deep connection between what time it is and where you are.
Mhm. What about the stars, the other stars, and the moon? Of course, we know that people throughout history have commonly used them, particularly at night, to orient themselves in space. But what about time?
Yeah, absolutely. You can also use the stars as a basis for timekeeping. They appear to be more or less fixed, but rotating more slowly than the sun, because as the Earth goes around the sun, of course, the angle that you have to look at to see any particular star changes. And those change over the course of a night. So you can look at exactly where a particular constellation is and use that as a marker to track time. They also change with the seasons. Particular stars are visible, just after sunset or just before sunrise at different times of year. This is the basis for one of the oldest calendars that we have really good information about, which is the Egyptian civil calendar. Was keyed to the rising of the star Sirius, which is the brightest star in the night sky, and it rises in August, just before the time when the Nile floods, which is the most important event in the agricultural year in Egypt. So that's what they took as their New Year marker. When this extremely bright star appears just before sunrise, then okay, we're right at the time when any day now the Nile is going to flood, and then our year starts, and we go from there. So you can use that as a marker as well.
Mhm. So, of course, astrology is not really something scientific, but it's still interesting to know where the cycle of the zodiac and the attributed zodiac signs come from. So, where does it come from exactly?
So the idea, basically, every culture, with a couple of exceptions that we know much about, has sort of this sort of 12 or 13 showing up in its calendar system,
Right.
and that has to do with the phases of the moon, right? So the moon takes a little under 30 days to go from one full moon to the next full moon, right? Or
Right.
one new moon to the next new moon, and so there's about 12 of those in a tropical year. And so, the cycle of the phases of the moon is a very convenient time scale for humans. It changes over a couple of days visibly, so you can tell where you are in that very easily. So people naturally gravitate to using that to keep track of what day it is. And then there's 12 or 13 of those in a year. And so you sort of everybody kind of ends up dividing the sky into 12 or 13 or 24 parts, and sort of
Right.
identifying patterns in the sky in that number. So the traditional the zodiac that we're familiar with comes from the Greeks and Romans. That's a 12 pattern division across the band where the sun and the moon and the planets appear. The Chinese system used to do 24 solar terms that they subdivided it a little more, but it's the same idea. It's about, one for the waxing moon, one for the waning moon.
And why is it that, for example, in our current calendar, the number of days per month vary, and why also the number of days in February varies every 4 years?
So the tricky thing about calendars, and a thing that makes the science of this really interesting and powerful, is that none of these cycles are integer multiples of one another. So the number of days in a year is not a perfect integer. It's 365 and a little less than a quarter day per year. And the number of days between full moons is not an integer. So if you're going to try and reconcile these things, you have to play some complicated games to get it to work out. One thing that people have done historically is called intercalation, where you have a year that has 12 months in it that are synced up with the full moon, but every 2 or 3 years you add a 13th month, and that keeps you in sync with the moon, but also keeps the months kind of in the right seasons of the year. The other thing you can do is you can define the number of days in a year and split that up into months of fixed length, and then just kind of forget about the phase of the moon. And that's the approach that the Egyptians took when they launched their calendar. They had 12 months fixed at 30 days each. And that's also the approach that the Romans took. They had months that alternated either 29 or either 30 or 31 days. And that comes out not quite the right number of days. You can get 365 days out of that, which is a little too short. So that causes the months to slip relative to the seasons by about a day every 4 years, which you can fix by adding a day to one of the months every 4 years. And that's the origin of the leap year system. This is implemented under the Caesars so it's called the Julian calendar reform, because it was first really put in place by Julius Caesar in the early BCE.
So let me ask you, looking at all the different calendars we've had across history, can we really say that one of them is better than the others at keeping track of time, or is that not really true?
What I would say is all of the calendars are good at doing a particular thing. And what they're doing is something that reflects societal priorities. So, for example, there's kind of 3 calendar systems in widespread use nowadays. There's the Muslim calendar, which is strictly lunar. I mean, if you're sufficiently devout, it requires somebody to sight the new crescent moon before you start the next month, right? And that gets you a 12-month year that is short by about 10 or 11 days from the tropical year. So the major holidays of Islam move through the year, right? The Ramadan falls in the summer sometimes, and then it's in the spring, that's in the winter, right? It moves around the calendar. The other extreme is the Gregorian calendar that we use in the West, which fixes the length of the year, but then has these months with fixed lengths that sort of alternate, but not quite. And you add a day every now and then to make sure that the solstices are always on June 20th or 21st and December 20th or 21st, and the equinoxes are in March and September, and that keeps those fixed. But then you have no idea, if you know what month it is, you don't know what the phase of the moon is. If you want to do both of those things, if you think it's important to both have a calendar that keeps pace with the seasons and to know about the phase of the moon, then you have to do something like the Jewish calendar, which has 12 months that are strictly lunar, but every few years adds a 13th month. And so that does the right thing, in terms of both knowing, if you know what month it is and what day of the month it is, you know approximately what the phase of the moon is. And also, what season that month will be in. Right, mm-hmm. that there are months that are winter months, and they're always winter months. There are months that are summer months. They're always summer months, but they might slide back and forth by 10 or 20 days. So sometimes we're coming up on Hanukkah. Sometimes that's after Christmas. Sometimes that's before Christmas. It moves around depending on where you are in the cycle of adding these extra months. So depending on what you think is most important. Right. So for religious reasons, the Muslim calendar prioritizes the moon over everything else. Mm-hmm. And they throw away a bunch of other information. That calendar works brilliantly for doing that, but isn't useful if you want to know what time, what day you should plant crops. If you just want to know when you should plant crops and don't care about the phase of the moon, the Gregorian calendar is brilliant. And if you want to know both of those things, you want something like the Jewish calendar, but it's very complicated then.
So could we say that it has a lot to do with the goals people have in particular societies, and perhaps also the practicalities of everyday life and what people choose to pay most attention to?
Yeah, absolutely. And what's really fascinating about this is we only have a couple of examples of calendars that come from way outside the Western tradition. Mm-hmm. Because the Chinese and India, they had very sophisticated calendar systems that are also pretty similar idea of months of fixed lengths. Occasionally you add one, they're kind of synced up with the moon, that sort of thing. If you look at something like the Mayan calendar in Central America, that is an empire that rose and fell before any contact with European civilizations. Right. They had this calendar that had a very different cycle to it. That had it's a 270-day cycle that is a 260-day cycle that is made by these sort of two sets of things. There's a name and a number that rotate, that increment forward as each day goes on. And we don't know what that was, but it was incredibly important to them, because they gave all their dates in terms of these two symbols for there are 13 numbers and 20 names, and we don't know why. We're not sure what it is that they were measuring with that 260-day cycle, but it's clearly very important to them. So different societies make different choices about what is the most important thing to base your calendar on.
Right. And what have been the roles played by things like politics and religion in the development and adoption of particular calendars?
Yeah, there's a lot of politics that goes into this stuff. So the Julian calendar reform that I mentioned earlier was done because the Roman calendar at the time was one of these intercalary calendars. Every few years, you were supposed to add a month. But that month was added on the authority of a priest that was also a political office. And so they started to play politics with this. Sometimes they would not add the month when they were supposed to because they wanted somebody of the other party to come out of office sooner, or they would add an extra, they would add a month in a year when they really shouldn't have, just to prolong the term of one of their allies. And things got really, really wacky, and the Caesars, had to sort of get it back in sync with the seasons and set up this more rigorous system. You also see this with religion. The Gregorian calendar that we now use is derived from the Julian, but is a small tweak to the leap year rule. Century years are generally not leap years unless it's divisible by 4.
Mhm.
And that happened because the date of Easter was shifting. If you have the leap year rule that's strictly one day every 4 years, you have a little bit too much, and then Easter was slipping relative to the seasons. And this was considered theologically incredibly important in the, medieval Europe, in the, sort of 1300s, 1400s. It had added up to a number of days that it was out of sync with the season. And people thought that was really important to address. And so they put together this commission of astronomers and mathematicians and came up with a way to change the calendar that fixes the length of the year a little better than the Julian leap year rule. And they did that essentially for religious reasons.
Mhm. So when it comes to keeping track of time, what would you say are some of the main differences between calendars and clocks?
I would say that, the difference between a calendar and a clock is basically just a difference of time scale, right? A calendar is, I would say, in very broad definition, is just a clock that ticks extremely slowly, right? The ticking of your calendar is a day, right? It's a clock that ticks once per day as you flip over to the next sheet of the day by day calendar page. Whereas a clock is something that ticks faster, on a scale that is useful for measuring time, for subdividing your day.
Right.
So,
And what are really the social functions of clocks? Because, of course, as we talk, for example, when it comes to calendars, there's political, religious, and social elements to them. What about clocks?
so I would say, with calendars, the obvious purpose is knowing when to plant things, right? So if you have an agrarian society, you need to know, okay, it is spring now, or it is going to be spring in a month. We got to get ready. We got to, get food in the ground so that we have food to eat, later in the year. So that's the obvious practical purpose of that. Clocks, the subdividing of days is something that becomes important once you start to get units of people that are, bigger than, a couple of families in a village,
Mhm.
right? If you start to have cities, then you kind of need to coordinate the activities of large numbers of people who aren't necessarily starting out in the same place. And you need a way to say, like, hey, you and I should meet, we need to do this thing together. We live in different locations. We should meet at some particular place. And, you want to be reasonably specific about when should you meet, right? And so you need some kind of clock, some kind of clock type system to be able to say, all right, the time at which we are going to meet is, when the shadow of this stick is in this position, then we're going to be at that place. And that, once you start trying to coordinate larger scale activities, you need that something that serves that function.
And what were the first clocks? What were the first devices that people used as clocks?
The oldest kind of clocks are undoubtedly sundials, right? So, you just have a vertical stick, you look at the position of the shadow. Those work great if you're in a place where it's sunny all the time. They don't work so well if you're in a climate like I am, where it's frequently kind of gray and dreary. And they also don't work at all at night. So the oldest kind of clock that can run under not sunny conditions is a water clock, which is just, you get some kind of container, you fill it with water, you put a hole in the bottom so the water leaks out slowly. And then you just, every time it gets empty, you fill it up again and let it empty out again. And, you can count the passage of time that way. Or you can take a container like that and put markings on it so that, you say, okay, when the water level gets to here, then 1 hour has passed. And when it gets to here, 2 hours have passed, and so on. And you can mark the passage of time that way with a water clock. And those date back thousands and thousands of years. There's a tomb inscription from Egypt around 1500 BCE by a guy bragging that he had invented a better water clock that compensated for the fact that the length of the day changes as you go through the year. And all it is it's one of these, it's an alabaster vessel that has lines marked on the inside, and there's just a set of lines for each month of the Egyptian calendar that are spaced slightly differently to compensate for the change in the length of the night. But this was, a amazing technical innovation in 1500 BCE, enough so that this guy brags about it in his tomb. So.
Right. And what about hourglasses? When did those appear, and what would you say, perhaps, because I haven't asked you about that yet, some of their limitations?
So one of the most surprising things I learned when I started looking into this history very seriously was hourglasses are surprisingly late. The first unambiguous depiction of an hourglass is in early 1300s. There's a fresco in the city hall in Siena, Italy, that shows there's an allegorical figure holding an hourglass, and it is a fully developed, recognizable modern hourglass. And that's the first time that we see something that's unambiguously an hourglass. People have stories about them being invented earlier, but there's no solid references prior to that. That's about the same time that you get mechanical clocks. So those two things are roughly contemporaneous. The big advantage of an hourglass is, it doesn't freeze, right? Sand, continues to be sand even when the temperature is very low. So, if you're in Northern Europe, water clocks are a little dicey because they can freeze over in the winter, and that's sort of a problem. But, a sand glass continues working. The problem is sand, if it's humid, it gets kind of clumpy and it doesn't flow smoothly, and makes a sand glass a little erratic. And so they take a long time to develop, basically because of material science. Somebody needs to figure out, how to make a sealed container that keeps the sand dry and flowing smoothly, and all that sort of thing. But they were the state of the art in timekeeping for a few hundred years. That was, sort of the most reliable method of keeping track of time. And, early mechanical clocks on ships, they would set using sand glasses. So, that was sort of the state of the art for quite a while.
Right. And you also mentioned mechanical clocks there. So how are they built exactly? What is it there that executes repeated motions and allows for us to reliably, or at least for our everyday activities, of course, in a good enough way, keep track of time?
Yeah, so the earliest form of mechanical clock is a thing called a virgin foliot. And so it's a bar that sort of twists back and forth, and it takes some amount of time to complete one oscillation of that, and that's what you're counting. And the way you both keep track of the count and keep it in motion is with a gear that's being driven by some force. So the traditional form of this is you have a big tall tower and you have a heavy weight that's falling slowly, and the cord on the weight is wrapped around the shaft of this gear. The gear is trying to turn, so it pushes a pallet that sets this foliot rotating, and then it turns a bit, and then there's a pallet that interferes with the gear and stops it. Which stops the twisting and then pushes it back in the other way, so it twists back. Then it stops it on the other side, and it goes back and forth and back and forth. That makes a very regular motion. It has a couple of problems in terms of the accuracy. One of which is it depends very much on the shape of the thing that's twisting back and forth. And it also depends on the driving force. So there's a historical example of this, dates to the 1300s in England and Salisbury, where they've reconstructed this virgin foliot clock, and if you wrap the rope around the shaft, that connects to the weight, if you wrap that rope around the shaft in a single layer, it ticks at one rate. And if you add a second layer of coils around it, it ticks slightly faster because you get more torque from having the effectively larger radius. So how hard you're pushing on the thing that's twisting changes the rate at which it ticks. So those clocks were never super accurate. They were, in fact, they tended not to have minute hands, right? So they tended to be, if you set up a clock face with one of those, it just had like an hour indicator because it wasn't very good for timescales shorter than that.
And when exactly did, after, of course, the development of the first mechanical clocks, when exactly did people start creating clocks that individuals could carry in themselves? Like, for example, I'm not sure if there's a more specific name to this, but pocket watches, wrist watches, and all of that kind of stuff.
Those are shockingly early. As pretty much as soon as somebody figured out how to make mechanical clocks, which is hazy. It's in that like 1200, 1300 sort of time range. Almost immediately, people started making them in all kinds of weird sizes and shapes. And so, you have these massive tower clocks in cathedrals that run for a very long time. You also have miniaturized ones, pocket watches that have, the little Virgin foliate system in there, this thing twisting back and forth. But the driving force is provided by a spring. So you get a coil of metal, you wind it up, and as it unwinds, that's what twists the shaft that keeps the foliate going back and forth. So people, by the late 1300s, people are making, watch-sized little clocks. They're not very good as these things go, and it depends a lot on the skill of the people who made them. There's a particular guy named Jost Berge, who I believe is Austrian, but who in the like late 1500s, early 1600s, really raises these clocks to a high art. Makes so the most accurate Virgin foliate clocks anybody ever made. But they were really variable.
So getting a little bit into the politics again, in what ways did the emergence of global empires and the need to keep track of time at high sea, for example, influence the evolution of clocks?
Yeah, the big issue with like globe-spanning empires is this question of longitude, right? That people at different east-west locations on the surface of the globe see different local times. Right. And that makes for some coordination issues, right? Like you and I are in very different time zones. So making sure that we get on this call at the same time is a little trickier than it might be if we were in the same village. But you can also turn that around and it becomes a problem of navigation. So knowing where you are on the Earth depends on knowing what time it is, and knowing the difference in what time it is where you are from what time it is someplace else. So that becomes a big issue because knowing your east-west position, if you're building an empire that requires sailing across the Atlantic or sailing across the Pacific, you really want to know when you're on those ships, like how much farther do we have to go before we're going to hit land? How much before we get to some place where we can refill our stock of fresh water, right? And so that becomes a big issue. Keeping track of time at sea becomes a big deal.
Right. And how did the development of astronomy as a scientific discipline contribute to the history of timekeeping? And also, was the development of astronomy in any way also influenced by these political and economic needs?
So in the case of the problem of navigation, right, there's two approaches that people take. One is just to build a really good mechanical clock, which turns out to be just a formidable technical challenge and is eventually solved in the 1700s. The other way you can do it is by doing astronomy. So you can make very careful observations of the position of the moon, say, relative to the background of stars. And if you can predict that position far enough in advance, you can use the position of the moon as a clock. You can say, well, okay, the moon is passing this star And I expect that to happen on this date at this time in London. And then according to my clock on my ship, it is now, the same date, but a different time. That means, okay, we're 3 hours away from London. We must be, this far across the Atlantic. And so that gives you a way of measuring longitude. And that works great on land almost immediately after the invention of the telescope. By the mid 1600s, people have nailed how to get time by looking at the moons of Jupiter through a telescope and making predictions about where they're going to be, tells you the time to within minutes, and you can make these great longitude measurements, and that's fabulous. It's a problem if you're on a ship, because the ship's pitching and rolling, and the moons of Jupiter are just a little too hard to observe if you're on the deck of a ship. But the moon is good for that. It's big enough and obvious enough that you can sight it pretty clearly even under bad observing conditions. And the problem with that is it's just really hard to predict the position of the moon. And so you need some of the greatest minds of their era to work on this. Isaac Newton comes up with his theory of gravitation and makes a model of the orbit of the moon, and how it should be affected by the gravity of the Earth and the gravity of the sun, and all of these orbits are elliptical, and puts all that together. Leonard Euler goes through and shows mathematically that Newton's system does in fact work, and that's all you need, and you can make these sort of predictions. And then there's a guy named Tobias Meyer, who's a German cartographer and astronomer, who just does the grunt work. He makes very careful measurements of the position of the moon over a period of several years, and he grinds through a ton of math to find all the parameters of the orbit that you need to use Euler's version of Newton's theory to predict the position of the moon. And that eventually enables people to make these nautical almanacs where you can look at where the moon is and say what time it is based on using the moon as a clock.
So earlier you mentioned why standardized time zones were developed or created, but are they really extremely accurate? I'm asking you this because sometimes, and I'm not sure if for good reason or not, people question and complain about why. I don't know if in the US that also happens between close states, for example, but here in Europe, why in Portugal we have one time zone, and in Spain just next to us it's UTC plus one. So I mean, are they extremely accurate, or there's also sort of a political ingredient there?
It's very much a matter of politics and convention. It's just convenient to have large geographic areas all have the same time, particularly now that we have sort of nearly instant communication between distant locations. Right. So, if it takes a day on horseback to get to the next town, it doesn't really matter if your clocks are, different by 10 minutes because of the position of the sun. Nobody cares. But if it's, if you can, in the course of a day, get, 1,000 miles away, well, then there's a big difference in the position of the sun at different times. And now you've got a significant synchronization problem. So, people decide to kind of do this on timescales that are sort of meaningful. So we pick a band that is about 1 hour wide. There's about the difference in longitude that is covered by 1 hour of time difference. So we just say everybody in roughly this band it's going to be the same time. But that does lead to, so in the US, it's sort of, Eastern Maine is kind of the farthest east that you get in the mainland US. And that time, we're pretending that the time of day there is the same as the time of day in sort of Western Indiana, which is quite a distance in longitude. It's about an hour difference, in the position of the sun. And that leads to some complaining, right? You have people in Indiana who are like, why are we changing time? Why aren't we on the same time as Illinois, the next state over? But, there's just got to be a boundary somewhere. Or else you have to have a system where, everybody says everybody just works on UTC, but then, you go to work at a different hour in Spain than in Portugal, and there's going to be a boundary somewhere where people are, just a few miles apart and behaving and, tracking time in a different way, and it's just going to be the way it is.
So for the last part of the interview, I would like to ask you some questions that are more within the realm of physics itself. So in what ways does the physical nature of time differ from our human understanding of it?
So the interesting thing is, as you start thinking deeply about these issues of coordinating clocks over long distances. So, I want to have a clock in Europe and a clock in the United States, and I want them to be synchronized with one another. You have to account for some fundamental things. You have to account for the fact that the light that's going to carry a signal back and forth between you travels at a finite speed. And if you don't account for that travel time, you get the difference in longitude wrong, or the clocks are improperly synchronized. So that's a thing that people worked out how to do in the 1800s. But if you think carefully about that process, it only works if everybody's standing still relative to one another. And it turns out if somebody's moving and watching you do this clock synchronization process,
right,
as they move past, they're going to say that you did that process improperly, because they're going to see the same speed of light, the signal going back and forth, but they're going to see it as, when the light's going in the direction that they're moving in, it's going to take a little longer. When the light's going in the opposite direction, it's going to take a little less time. They see a different time, and they see your clocks improperly synchronized. And it turns out thinking about that difference is a way into the theory of relativity. That tells you that that's a real thing, that people who are moving relative to one another will not agree that their clocks are properly synchronized. And in fact, they'll see the other person's clock ticking more slowly than theirs. Right. And that's an absolute fact about the universe that we can verify experimentally in a bunch of different ways. And that has really deep consequences for the nature of time. It also ends up mixing together time and space. So, you see this difference in times. You also see a contraction in length. So people who are moving relative to another will measure a different separation between objects in ways that are also, it's absolutely predictable. It's 100% verifiable. And that's a very real thing. And there's sort of a trade-off between these, right? You see less time passing. You also see less of a distance in space, and these things balance each other out. And so you can work this out and show that time is intimately connected to motion, and then that it's also connected to position because of the effects of gravity. And so gravity also changes this mix of what is space and what is time at different locations. And that has a really profound reshaping of our understanding of the nature of space and the passage of time.
And does the way we keep track of time, is it in any way similar to, I'm not even sure if this question makes sense, but is it in any way similar to how time actually runs?
So there's a whole bunch of ways to answer these kinds of questions about the nature of time and what it's time. And it depends on what kind of physicist you talk to. So there are people who do sort of general relativity and cosmology and think about sort of deep time and long, spans of time, and think about really have to grapple with the nature of time as one component of a four-dimensional space-time. And then they'll have a different sort of answer than someone who's in the business of making clocks. I'm closer to the making clocks people. So my feeling is that time is what you measure with a clock, right? I'm going to have some process that I say, this is my unit of time, and I'm going to count how many times this process happens, and that tells me how much time has passed. And then that's a very individual thing, because as you move around, right, different people's clocks are ticking at different rates and so on. But my inclination is to say that the time that you experience, as measured by a clock that you carry, is the thing that's most meaningful. But people who do, sort of general relativity, cosmology sort of things, will approach this somewhat differently.
Right. So there's one type of clock that is more recent we haven't talked about yet. What are quantum clocks and how do they work exactly?
Yeah, so the modern standard of time, as I said earlier, is based on quantum mechanics. So, when an electron in an atom changes from one state to another, it absorbs or emits light, and the
Right.
frequency of the light that it absorbs or emits depends on the energy difference between the states. So we have chosen a particular pair of states to be our basis of time. It's two states in the cesium atom. And those two states are separated by light that by definition has a frequency of 9,192,631,770 hertz. Full stop, right? Decimal point, infinite number of zeros. It's defined to be exactly that. And then the clock that we use is a microwave source in the laboratory that's tuned to exactly that frequency. And we use the atoms, so the atoms in an atomic clock are there as a reference. And so we are basically shining these microwaves on the atoms and saying, is this exactly the right frequency that you want to absorb? Yes or no, which we measure by did they change state or not. And the answer to that then lets us adjust the frequency of the microwaves to, more perfectly match the frequency that the atoms want to see. The nice thing about this is there aren't any physical moving parts, right? The microwaves are oscillating electromagnetic field. You can pick that up. The atoms, every cesium atom in the universe is identical to every other cesium atom in the universe. So it's not like you're not dependent on, who made your clock in the same way. That these atoms are perfect little references, and the ticking of the microwaves is a perfect clock in some sense. And so that's the basis for timekeeping. We have this incredibly fast oscillation, and it turns out to be convenient to work with electronically, so we can measure those microwaves and sort of divide that frequency down to get something that ticks once per second in a fairly easy way.
So what are some of the main applications of this type of clocks? I mean, what activities in modern industrialized and post-industrial societies we wouldn't be able to perform as accurately without the use of these clocks?
Yeah, the killer app for atomic clocks is the global positioning system. So if you ever make use of Google Maps or Apple Maps or whatever sort of smartphone you have that you navigate with, or if you're someone who plays like these dopey little augmented reality games, there's Pokemon Go on my phone, that depend on knowing your position. That's based on atomic clocks. So the global positioning system is a network of satellites orbiting the Earth, and those satellites have extremely well-defined orbits, and they each satellite contains a clock and just broadcasts its time. It sends out a coded signal saying, I'm this satellite and it is this time. And the receiver on your phone picks that up. And because we know how long, we know what the speed of light is, if you know how long it took the signal from the satellite to get to your phone, then you know how far away you are from that satellite. And you can pick up the signals from 4 different satellites, compare them to each other, and work out all of those delays. Work out, okay, so this one is delayed by this many nanoseconds, this one's delayed by this many nanoseconds, and then determine all those distances to within a few meters. And then that fixes your position on the surface of the Earth. Right, so you're then you're sitting at the point that is the intersection of 4 spheres centered on these particular satellites, and that they intersect at only one place on the surface of the Earth.
Right.
So that to do that, right, to be useful, you want to be able to know your position to within kind of. For navigation, you want to know to kind of, the width of a road, right? So, maybe, 3 meters or something like that. That requires time, timekeeping that's good to nanosecond precision. The one and only area where American units are superior to the metric system is the distance that light travels in a nanosecond is almost exactly 1 foot. So, 12 inches, 1 foot is the distance that light travels in a nanosecond. So for every nanosecond of error in your timing, that's a foot of position error. So it's about 3 nanoseconds to the meter. And so you need your clocks to be that good, and the only clocks that are that good are these atomic clocks. And so we've got them in satellites. The global positioning system is the big one. That's an American system that was originally put up by the U.S. military, and now it's maintained by the U.S. military, but it's open to civilian use. There's a Russian equivalent network of satellites. The Chinese have started putting their own together. There are these different, but they all have the same basic principle. Atomic clocks and satellites determine the distance from you to several satellites. That fixes your position on the surface of the Earth.
Right. So I have one last question then. Do you have any idea, or is it possible to predict what kinds of clocks, calendars, and other potential timekeeping technologies would be developed in the future?
So there's a lot of work going on now, right? We have these cesium atomic clocks are good to a level where if you have 2 of them and you ran them continuously, they would need to run continuously for something close to 1 billion years before they would drift apart by 1 second, right? So they're incredibly good. And most people say, well, why do you need anything better than that? But people are in fact working on clocks that are much, much better than that. So one reason is you could do GPS better, right? You can make better atomic clocks. You could, measure your position on the Earth to centimeters, and then you think about autonomously moving robots and that kind of thing. You can also just use it to measure positions and measure things incredibly accurately. If you have clocks that are kind of 1,000 times better than that, you can also do some really interesting things with exotic physics. And so, I mentioned briefly that gravity affects the rate at which clock ticks. So something like a gravitational wave passing by causes this very minute stretching and compression of space-time as it goes by. That also causes, a speeding up and slowing down of a clock as that gravitational wave passes. So if you had a network of phenomenally accurate atomic clocks, you could see a passing gravitational wave as sort of a ripple in the time signals from these clocks passing through the network. And so people have proposed doing this, putting next generation atomic clocks that are 1,000 times better than the cesium standards. If you put those on satellites and you put a whole bunch of them out in orbit, you could use that to track gravitational waves and tell you something about the fundamental physics of the universe, this very exotic kind of physics. The principle for those kind of clocks is still essentially the same as cesium atomic clocks. You have 2 energy levels in an atom. You're driving an electron from one to the other, and it absorbs or emits a particular frequency of light, depending on which 2 levels you've chosen. You're just choosing a different set of levels. You're choosing levels that are separated by frequencies that are thousands of times bigger than the microwave frequency for cesium. And so they're, visible light or even ultraviolet light in the transition. So you're using lasers and stuff. But we have these just astonishingly good techniques for measuring these clocks, and they're good to position. They're good to levels of precision that are 10 or 100 times greater than the best cesium clocks right now. And people just keep pushing this forward because you can do these exotic physics things with them.
Right. So the book is again a brief history of timekeeping, the science of marking time from Stonehenge to atomic clocks. I will be leaving a link.
That's the US version. There's a different cover for the UK.
Yeah, and I will be leaving a link to it in the description box of this interview. Dr. Orzel, just before we go, apart from the book, would you like to mention where people can find you and your work on the internet?
On the internet, I have a blog on Substack, blog, newsletter, whatever you want to call those. And I'm on Twitter as long as that lasts, and Facebook. And if you just search my name, I'm the only notable Chad Orzel in the world. So if you search it, you find me pretty quickly.
Great. So I will also be leaving some links to that in the description box of the interview. And thank you so much again for taking the time to come on the show. And your book is really fascinating, so I recommend it to everyone who will be watching and listening to this interview.
All right. Thanks very much. This is fun to do.
Hi guys, thank you for watching this interview until the end. If you like what I'm doing and to keep the channel sustainable, please consider supporting me on Patreon or PayPal. All of the links are in the description box of this interview. Otherwise, and if you like what I'm doing, please share it, leave a like and hit the subscription button. This show is brought to you by Einlights, Learning and Development Done Differently. Check the website at einlights.com. I would also like to give a huge thank you to my main patrons and PayPal supporters, Karen Litska and Blanchett Perga Larson, Lau Guerrero, Francis Ford, Hans Frederick Sunder, Ricardo Vladimiro, Craig Healy, Adam Castle, Olaf Alex, Jonathan Wiesel, Jacob Klinkby, Matthew Whittingbird, Arno Wolf, Tim Hollis, Ian Ricalania, John Connors, Paulina Barron, Philip Force Connolly, Jerry Mueller, Herbert Gintis, Rutger Voss, Wo Weingard, Rebecca Newberger, Goldstein, Dan Demetrio, Robert Windiger, Rui Narcio, Arthur Coe, Zup, Marco Neves, Colin Holbrook, Susan Pinker, Bernardo Seixas, Pablo Santurbano, Simon Columbus, Jorge Espinha, Phil Kavanagh, Corey Clark, Mark Blythe, Roberto Enguanzo, Michael Stormir, Eric Neumann, Samuel Andreev, Tiago Nunes, Bernardini, Alexander Dunbauer, Fergal Cusson, Ivan Bodrenko, Paul Herzog, Don Ross, Jonathan Librant, Haslem Bullet, Nathan Nguyen, Stanton T., Samuel Correa, Eric Hines, Mark Smith, J.W. João Eira, Tom Hummel, David Sloan Wilson, Yacila Dez Araújo, Romain Roach, Dmitry Grigoriev, Diego Antonio Correa, Tom Roth, Yannick Punter, Adana Rusmani, Charlotte Bliss, Nicole Barbaro, Adam Hunt, Pavel Ostazewski, Nelek Bach, Catherine and Patrick Tobin, Al Ortiz, Guy Madison, Gary G. Hellman, João Linhares, Lida Cosmides, Saima Afzal, Adrian Yegi, Nick Golden, Paulo Tolentino, João Barbosa, Jules Price, Edward Hall, Edin Bronner, Franca Bortolotti, Gabriel Pons Cortez, Ursula Litzke, Dennis Cook, Scott, Zachary Fish, Tim Duffy, Todd Shackelford, Sonny Smith, and John Wiseman. My producers Cesar Webb, Jim Frank, Lucas Stafiniak, Luis Caetano, Tom Wagner, Dan Curtis Dixon, João Linhares, Benedict Mueller, Vega Guidi, Sardus Francis, Thomas Trumbull, and Nuno Welder, and my executive producers Michel Rugieski, Rosie, James Pratt, Matthew Lavender, Sergio Quadriano, and Bogdan Kanivets. Thank you for all.